I went through my entire time on Earth empowering and unequivocal. Additionally, the universe hypothesis. At last, the hypothesis is being tested. I welcome that, since that is the way we push ahead. That is how we gain ground in science. The James Webb Space Telescope is upsetting a remarkable measure of what has been seen as truth in cosmology. For the new year, another ultra-deep image demonstrates that we have errors in cosmology. The instrument that ought to demonstrate to us the primary stars of the universe is becoming a foe of the past perspective and may present to us a thoroughly astounding science. Not all experts are quailing in dread at the new realities. Other well-informed specialists welcome the progressions since it has been clear for a very long time that something was the matter with our old theories. The deviation in the evaluation of the rate of progression of the universe alone should have shaken special perception in the past. Yet, taking everything into consideration, they stuck to old theories about the universe. CMB, cosmic microwave background, radiation, considered the most settled light in the universe, was made something like 380,000 years after the Big Bang, exactly when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Researchers call this interaction reionization, which made the universe able to be lit by the CMB. The CMB was first seen by Americans in 1964, physicists Arno Penzias and Robert Wilson, while they dealt with a different type of radio-receiving antenna technology. This revelation was, for a long time, seen as possibly the most robust piece of proof for the theory of the old Big Bang, earning Penzias and Wilson the Nobel Prize and an unquestionable spot in the history of astronomy. The CMB most likely offers a viewpoint on the early universe, with little temperature contrast providing fundamental information on the conditions not long after the Big Bang. Specialists included the CMB as a solid foundation for fundamental evaluations of the physical universe, to check the progression speed of the universe, among other things. The cosmologist Edwin Hubble had already settled this in the late 1920s, finding that galaxies far away flee from us and that their speed is in line with their distance. Today, these observations are referred to as the Hubble law or the Hubble constant. Hubble didn't have the high-level surveying techniques available many years later, at the point when the CMB was found, which led to a recalculated development rate. These were all around lower than Hubble's original figure. Later, experts recalculated the rate utilizing type I supernovae as standard candles that provide steady light, which could be used as a dependable measuring point. The estimates within the CMB resulted in a development rate of around 67 kilometers per second per megaparsec, while estimates using astronomical blasts yielded around 74 kilometers per second per megaparsec. What does this divergence in determining the advancement speed of the universe truly tell us? Did you know that this discrepancy has been known since the 1990s? Since that point, analysts have known, or at least thought, that something may be the issue. The investigation of the CMB, the methods of evaluation, or the possibility of the universe's extension. The abnormality between the observed and predicted values of the development rate is known scientifically as the Hubble tension, or S8 tension. The ramifications of this strain are tremendous, showing that fundamental aspects of our understanding of the universe may be imperfect. For a long time, specialists were puzzled. Since the James Webb Space Telescope started working, it has furnished experts with stunning data that may now reveal information on the issue of the rate of advancement of the universe. Some systems are so old and mature that their advancement should have begun, hypothetically, before the Big Bang, disrupting old cosmology. Analysts no longer discuss mistakes or evaluation contrasts. They discuss the emergency in current astronomy. Not only could the improvement rate be off, but the entire idea of expansion, or the Big Bang itself, is being put into doubt. Pictures from the telescope provide proof of a universe completely different from what we have long thought. The Hubble tension was the chief challenge to specialists who still have confidence in old speculation. Now, they face a dilemma. Do we actually comprehend the universe? Various researchers now view the relics of their previous brilliant source of both discovery and torment, exploring space with fear and wrestling with what they find. Taking into account the emergency in science, we should ask ourselves, what do we, in fact, know about the universe? To answer this, we truly need to comprehend how science works. Speculative experts utilize a multifaceted plan of mathematical models, careful data, and logical reasoning to draw conclusions from the general to the specific. Their understanding comes from a blend of observational data, theoretical insights, and mathematical calculations. The term theory alone shows that these are advancements and ideas that are not absolute facts. The primary critical data we have come from photographs and telescopes, the accumulation of waves and radiation. With the most recent radio telescopes, data from neutrino studying systems, or gravitational wave detectors, we now have more tools than ever. With the James Webb Space Telescope, we now have an instrument that can split light into individual frequencies and analyze it in incredible ways. Webb can show us the essential parts of galaxies in the early universe, how much mass they contained, how many stars were present, and how they evolved. However, Webb has limitations, such as the inability to continually determine whether we are seeing galaxies or, on the other hand, black holes with immense gravitational forces that emit as brilliantly as a galaxy. We must face the reality that, for a long time, our science has accepted too many possibilities as facts while dismissing alternative explanations. Research has long been confident in its accuracy, but the most recent discoveries from the James Webb Space Telescope signal that it is time to replace theories with new insights, as has happened throughout history in science. Experts are looking forward to these new discoveries, which are unexpectedly astounding and diverse. Scientists are now attempting to develop new explanations, but the foundations of our understanding of science are being shaken by these revelations, disturbing many specialists. The most recent versions of real science are still largely founded on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the foundation of our understanding of the physical world and the universe for a long time. Newton's principles described the movement of objects under normal conditions and function particularly well on Earth. However, in space, his theories required further development, something that was accomplished by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, changed how we interpreted reality, showing that events are relative to the observer's frame of reference. This theory introduced the concept that time and space are interconnected, forming what we now call space-time. It also established that the speed of light is a constant in all frames of reference, fundamentally altering our understanding of motion, gravity, and the structure of the universe. Einstein's later work, The General Theory of Relativity, published in 1915, took these ideas further by explaining gravity not as a force, as Newton proposed, but as the curvature of space-time caused by mass and energy. This was revolutionary. It allowed scientists to predict phenomena such as the bending of light around massive objects, gravitational lensing, and the existence of black holes, predictions that have since been confirmed by observation. However, even Einstein's theories, as groundbreaking as they were, are now being challenged. The James Webb Space Telescope has provided images of galaxies and structures that seem too old, too massive, and too developed to fit within our current cosmological timeline. If the universe is indeed expanding according to the Big Bang model, we should see younger, smaller galaxies in the early universe, not the mature ones Webb has revealed. This has led some physicists to question whether our fundamental understanding of cosmic evolution is flawed. Could it be that the universe is not expanding in the way we thought? Are we missing a critical component in our models, such as unknown physics beyond our current theories? Some scientists propose modifications to dark matter and dark energy, two mysterious components that supposedly make up around 95% of the universe's total mass energy content, but remain undetected directly. Others suggest that new physics might be required, perhaps an entirely different theory of gravity that supersedes Einstein's. If these questions remain unresolved, we may need to reconsider not just the expansion rate of the universe, but also the very framework that supports modern cosmology. The crisis in our understanding is not just about small errors in calculations. It is about whether the foundational principles we have relied on for a century still hold true. The future of cosmology. Where do we go from here? The scientific method demands that when evidence contradicts established theories, we must be willing to modify or even abandon those theories in favor of better explanations. The James Webb Space Telescope is forcing scientists to confront this challenge. As more data comes in, we may soon witness one of the most significant paradigm shifts in the history of physics. This could lead to a revised model of cosmic evolution that explains the unexpected structures observed in the early universe. A new theory of gravity that extends or replaces Einstein's general relativity. A deeper understanding of dark matter, dark energy, or even unknown forces shaping the cosmos. The possibility that our universe is part of a larger, more complex multiverse. The search for answers continues, and as it does, the field of cosmology stands at the edge of a new frontier. The discoveries being made today could redefine what we know about the origins, structure, and fate of the universe. One thing remains certain. Science thrives on questioning assumptions, testing hypotheses, and adapting to new discoveries. The James Webb Space Telescope is not just an instrument for observing the cosmos. It is a catalyst for change, pushing humanity closer to uncovering the true nature of our universe. One another, and based on the movement of the observer, his publication of the general theory of relativity. This idea was extended in 1915 with mathematical representations of the characteristics of gravitation, based on mass-like curvature of space-time. Einstein's theories regarding stars or galaxies were significant in many areas. However, he was aware of their limitations. He knew his theory would never fully describe the universe and longed for a unified theory, which he never achieved. No other expert has reached this stage either. Wouldn't it be fascinating to learn about its location? Makaku, an unmistakable astrophysicist from the United States, stated in an interview that this issue would undoubtedly win a Nobel Prize. Could we investigate whether experts might have missed potential misinterpretations or whether the blame lies with telescopes? Dark energy and dark matter exist at the top of the suspect list for the crucial reasons behind the emergency in cosmology. Our developing models of the universe include concepts about dark matter and dark energy, which make up around 95% of the universe. However, neither has been clearly observed, and their confirmed presence has never been demonstrated. They most likely do not exist in any known form or shape, necessitating additional explanations for the universe's expansion and dynamics. On the other hand, they could have properties we don't yet appreciate. One thought is that the true properties of dark matter and dark energy have changed over time, possibly displaying some kind of evolution. Another hypothesis suggests that gravity itself needs to be put to the test. The force of attraction through mass or curvature in space-time has not yet been fully explained. The ideas behind space-time, discovered by Einstein and traditionally upheld, may require revisiting. We can't rule out the possibility that gravity has unexpected properties or that another force is responsible for the attraction between objects. Over time, a few constants have been established in cosmology and astronomy as universal principles. The study of the universe has always been a journey defined by our constant search for understanding and discovery. From ancient human civilizations observing the stars to modern space telescopes exploring the depths of the universe. Each step toward improvement in theory has revealed new mysteries while challenging established beliefs. In the realm of cosmology, the James Webb Space Telescope, JWST, remains a beacon of scientific advancement, promising to alter our interpretation of the universe's origins and evolution. Launched with remarkable capabilities, JWST represents a breakthrough in observational space science, designed to investigate the universe with unprecedented accuracy. Examining radiation, the cosmic microwave background, CMB, often referred to as the light from the Big Bang, provides insight into the universe as it existed shortly after its formation. This ancient form of radiation carries fundamental data on the origins of the universe, including temperature variations crucial to understanding the development of galaxies and large-scale structures. The disparity in the calculated values of the Hubble constant, known as the Hubble tension, has been a subject of prolonged debate. It suggests that something is wrong with our basic understanding of the universe and its early structures. Discoveries challenge conventional theories and require a reassessment of whether our perspective on cosmic expansion is fundamentally flawed. New insights might uncover hidden parts of the universe's creation, raising questions about dark matter and dark energy, two mysterious components that make up most of reality. The progression of science depends on the ability to reshape our theories in light of new evidence. JWST exemplifies this pursuit. Its discoveries will serve as a foundation for future cosmological discussions and shed light on new perspectives on the universe's mysteries. The future of cosmology might witness tremendous changes, leading to significant implications for how we understand the universe, from its existence before the Big Bang to the ongoing processes that define its fate. The solution to the most pressing, limitless questions may lie beyond our current knowledge, and JWST's observations may ultimately be crucial in revealing new insights that could reshape how we interpret reality itself. The way forward for cosmology and space science is filled with potential. Each novel observation and piece of data from telescopes like JWST brings us closer to answering the most significant questions humankind has ever asked. How did the universe begin? What is its ultimate fate? Are there other forms of life out there? Or are we alone in this immense universe? These are questions that may one day find answers, and the James Webb Space Telescope has been at the forefront of this great effort. Probably, the future of cosmology will involve a combination of new technologies, refined theories, and momentous revelations that continue to push the limits of what we know. As we venture further into the unknown, science knows one thing for sure. Like the universe itself, our knowledge is always in a state of constant expansion, driven by the search for information, discovery, and the miracle of revelation.